Good afternoon. Actually, it's almost midnight. I'm going to show some data from models where the simulation time frame covered that of the cruise. That was September 30, 2013 for MAR555. If I have time, I'm going to try to show some of the observations that Miles processed. Hopefully I have time to do that. I'm going to recap some of this in class as well, but it's easier if I can work at my own pace here. So what we're looking at is a chunk of the Northeast Coastal Ocean forecasting system. That is a hindcasting forecasting coupled ocean atmosphere and wave model developed by Dr. Chen here at UMass Dartmouth. It's online. The data is online. You can look at NECOFS, N-E-C-O-F-S. Just Google that. So I grabbed the hindcast. So the model essentially forecasts forward in time, and as time progresses and observations come in, it redoes the model calculations, including the observations for a more accurate estimate of the ocean, wave, and atmospheric circulation. So this is the hindcast component. The model essentially is run at a time after the event of interest occurred. So we're looking at just one day, September 30. I'll be covering as much as I can from the model. I just grabbed just the Buzzards Bay data. The data from the model is very big, very cumbersome and difficult to work with, so I just cut out essentially Buzzards Bay, which is what you're looking at here, just because it's easier to deal with much smaller data. So this is a piece of NECOFS. You can see here, I don't know if it'll show in the video rendering, depending on the resolution, these little grid lines. In each of these little triangles, essentially what the code FECOM does is solve the conservation of mass and momentum. And you can imagine stacks of these triangles going down to the bottom. I'll show you a slice transect through the grid later so you can have a sense of the vertical structure. This is the horizontal structure. And what this allows you to do is you sort of place the triangles, larger triangles where less things are happening slower, and smaller triangles where they're happening faster, in this case driven by coastal features. In other cases, when we look at the wave data, you'll see the high resolution near the fronts, the tidal mixing front, the shelf break front, and that was essentially designed by Chen in a trial and error effort to try to optimize the length scale distribution in the model. So here you're seeing length scales ranging from roughly 40 meters up to, in this model, close to probably 200 or 300 meters here. This is Buzzards Bay. I have a split screen here, so I'm going to try to work with that. I'm going to just expand it out a little bit here so you can have a sense of it. We'll get to the edge of what I cut out pretty soon here. And let me shut off the grid here. So we're looking at the bathymetry in meters. I also put the contours in because I want to note some important things. Up here, hopefully my mouse will show up, is Cape Cod Canal. And that obviously was artificially dug in the 20s. And then finished up by the Army Corps in the 30s, and that connects Buzzards Bay to Cape Cod Bay. It's an artificial connection. The main connection here is to Rhode Island Sound. This is essentially the mouth of the bay, where the deep water of the bay is. These are the Elizabeth Islands. They're private islands owned by the Forbes, with the exception of Cuttyhunk right here. And in between the islands, you have these, what they call these holes. I'll show later the sea surface elevation on this side and this side, basically the tidal elevation differences. Primarily in amplitude between Buzzards Bay and Vineyard Sound. Over here the red indicates that Vineyard Sound is deeper. It's typically about 30 meters deep. Buzzards Bay is much shallower. Buzzards Bay average depth is about 11 meters. There are a few places where you have deep holes closer to 20 meters, but again the average depth is 11 meters. It gets shallower as you move up towards the head of the bay. And an important distinction about the bay is that the shallow, as you move across the bay, the depth on the west side, or our side of the bay, is shallower than on the east side. I put a line across. This graph indicates the bathymetry going across the bay. You can see the deep sections over here at 15 meters are on the east side of the bay, closer to the Elizabeth Islands, and the shallow sides here. So it's asymmetrical left to right looking up the bay in terms of depth. So shallow on the left and deeper on the right. And that's actually a glacial origin. And so most of the exchange is down here, but because the holes are vigorous water exchanges, it does influence the water properties of the bay, particularly in the east sections of the bay. And we'll see that in the model results, and I think we see that as well in the observations. Vineyard Sound has very vigorous tidal currents, so the water properties here are strongly reflective of oceanic water properties. So it tends to be, well, depending upon the time of year, it definitely takes on a higher salinity, and in the summertime it's generally colder water. Buzzards Bay is quite shallow, so it responds very strongly to the heat flux, so it gets very warm and very cold, because you're essentially you're driving heat flux in and out of a shallow basin that has some level of flushing, but relative to its depth, the local surface heat fluxes still exhibit some control on it. Trying to think if there's anything else to say. Just to orient you, here's S-mast 1, and the red triangle will be, in at least all my Buzzards Bay shots, the Lucky Lady path. So as I go through the day, this is in timestamp on there's in daylight savings time, Eastern daylight savings time. As we move out into the day, we left the dock at about 8 o'clock, and then we progressed out into the bay. Now the model saves every hour, so you don't see a nice smooth path. You just see where the boat was on the hour throughout the day, and then we turned around and came back. And so we basically did roughly a cross bay excursion, and then eventually ran out of time over here and didn't quite get Station 5 in, and returned back here. Trying to think if there's anything else I want to hit here. I guess I'll mention one other thing while I'm here. There are some rivers that dump into the bay. Of course, the Acushnet. There's several rivers up in Wareham as well, and in Dartmouth. Relative to the flushing in the bay, the freshwater doesn't introduce much in terms of buoyancy. And so there are some estimates of the buoyancy-driven flow, and it's quite weak. So it's often referred to as an estuary, but I don't know if we can technically call it an estuary in that sense. There are parts of the bay which certainly can be considered estuaries, and perhaps that's what people are referring to. But the estuarine-driven circulation, the salinity-driven circulation, compared to tides and wind and everything else, is quite weak. And the other thing I'll mention now is that this is a piece of a much, much larger scale model. When I show you the wave solution, you'll see the entire domain of this model. Actually, that's a lie. This model is essentially the entire Massachusetts coast. This is just a piece of it, and so and it actually wasn't I think the main crux of this was actually Mass Bay. So we'll see that not all the rivers are represented, and other things like that. And no models are perfect, except for this one. I guess that is about it.